the refrigerant goes in a loop. It goes from the compressor to the condenser, through an expansion valve, and through the evaporator. We know that we have a high pressure side. Pressure is high here, and the pressure is low there. They'll talk about the evaporator pressure. That's low pressure. They'll talk about the condenser pressure. That's the high pressure. Okay? The pressure gain across the compressor and a pressure loss across that expansion valve. But what throws students for a loop or so that's hard to understand is why is state 4, which is saturated liquid, relatively warm, and why is, 3 is warm, and why is state 4 cold? Is there a lot of heat transfer out of the refrigerant when it flows through the expansion valve? No, there's not. Hold it. It goes in warm, comes out cold, and there's no heat transfer to make it cold? That's not possible, is it? Well, without this class, without the study of thermodynamics, you're right. This doesn't make sense. But it does make sense now that we've studied thermodynamics, doesn't it? To explain this, what you really need to have is a good grasp of the pressure-temperature diagram. So what is the pressure-temperature diagram? Have you seen the pressure-temperature diagram before? Everybody puts their hand up. Absolutely, Professor. What chapter of this textbook? 3. Yeah, right? All about that. What was it a projection of? It was a projection of the PVT surface. And you have a projection, all substances you can plot. You have a point right here and a point right there, a line in between the points, another line scooting up like this, and a line going down like that. What are the names of those 2 points on the PT? That's exactly right. We have the triple point and the critical point. What was the idea behind the triple point? All 3 phases at that unique temperature and unique pressure can coexist in equilibrium. You mean solid, liquid, and vapor can coexist in equilibrium? Yep, at that triple point. What about the critical point? What was the unique idea about the temperature of the critical point and the pressure of the critical point? It's where you lose the distinction between what's a liquid and a vapor. Above that, your supercritical fluid. Essentially, out in this region, a lot of times I'll draw it like this, but it's not all that clearly. This is supercritical. The substance is a state of being supercritical. What does that mean? Well, in the presence of gravity in a little glass jar where I can look in and see the fluid, I don't see liquid settling to the bottom and vapor settling to the top. It looks like a mushy cloud. Because if I have water in a glass jar like this, and it's just pure water in there, water vapor is going to be at the top and liquid water will be at the bottom if I have a 2-phase mixture. But above that, I will not have a 2-phase mixture. It'll look like a mushy cloud, if that works. Okay, now where are the 3 regions of single-phase behavior of the substance? Where is it all a vapor? Where is it all a liquid? Where is it all a solid? Yeah, so off in this region, it's all vapor. What about all this region? Liquid, and all this region, solid. And the big takeaway is that it coexists in equilibrium where there's liquid vapor. And so basically these are states where they coexist in equilibrium, and then that's where it would also change phase. If maybe I start here. Let's do this. Let's put some numbers down for water. Do you like water? Are you familiar with water? Yeah. Okay. What is the triple point temperature in degrees C for water? Around 0.01 degrees C. What's the critical point temperature for water? Oh, about 374 degrees C. There's a big difference between the two. There's another point of very special interest. It's called the BP, the oil spill point. No. It's the boiling point, right? Isn't it the boiling point? Now, what's the temperature for the boiling point of water? 100 degrees C. What's the pressure for the boiling point of water? 1 bar or 101 kilopascal, right? Okay, now what is the pressure for the triple point for water? Around 0.6 kilopascal. What's the pressure for the critical point of water? Way up here, it's around 22 megapascals, so it's around, what is that, 2,200, 22 megapascal, convert that to kilopascal, 22,000 kilopascal. When they have such huge range of pressures, they often put this on a log plot for pressure. Okay? But let's not get bogged down if it's, because it'll make the line look straight. Otherwise, there's a significant curvature to that. But what happens is, think about this. This is a review from Thermo 1. Let's say I tell you that my water is not 100 degrees C, but it's only 20 degrees C. Okay, it's somewhere around this line. And I tell you that it's at a pressure of 101 kilopascal. Where is it at? What is the substance? What's the state of the substance? It's smack dab in the liquid state, isn't it? Let's say that it's 220 degrees C and it's 101 kilopascal. Where is it at? It's out in the superheated vapor state, right? And so what happens is if you move from here to there, what's happening? Either you cross the line either way at constant pressure, constant temperature. Most people like to think of crossing a line as I'm at constant pressure and I'm increasing temperature horizontally. What's happening? I am undergoing a change of phase from liquid to vapor. Oh, it may sit there a while until it goes from a quality of 0 to a quality of 1, absorbing a lot of energy. So you have this whole idea that these are a sequence of equilibrium states. So if I'm in equilibrium, let's say I have a saturated liquid and I'm at relatively high pressure right up here, okay? Then I drop the pressure, okay? Well, it probably would like to drop down into the vapor state, wouldn't it? But if it's saturated liquid and I drop the pressure, I just can't vaporize it for free, right? There needs to be some energy in which to break those molecules apart and put them in the vapor state. Where's that energy come from? It's not coming from the surroundings. No heat transfer from the surroundings. So what happens is it tries to crawl back to this line and scooch down that line. I messed this up a lot. Let me go to another one. It's going to start here, the saturated liquid, right? If I want to drop the lower pressure, it'll actually scoot along this line, staying in states of equilibrium, actually constant enthalpy. So what happens is some of the liquid will flash, meaning very rapidly go into the vapor state, flash. What a lot of the other liquid, or the remaining part of the liquid, will be at a lower temperature, and the whole mixture will be at a lower temperature. So what happens is let me back up here, is let me do this, is there's intermolecular forces that exist in a liquid. They're not the forces which are intramolecular forces, which keep a molecule together, but they are the forces that keep a liquid together so that the molecule-to-molecule attraction. And when you pump heat in, then you can break it, make it go into the vapor state, and that's what you're doing. You're breaking that type of bond, that type of attraction. So the intermolecular forces are the stick-togetherness of the liquid. And so you need to have some energy. Where does it come from? Well, from one pocket to the other pocket, so to speak. From one part of the, so the whole thing will go down in temperature. Some will remain liquid, some will remain vapor, but the total energy of the system didn't change. And that's what makes it cold, right away cold. You can take a look at the properties of refrigerant. I was going to go and show you out there on the website. There's some places where they do a pretty good job of putting out properties of refrigerants. Here's a Purdue University publication. It's a little old, but they were tabulated the properties of the refrigerant like 134A. You can look at some of the numbers that grabbed out of that website for different values of pressure, temperature, critical point, and then you know what's happening. It's coming in saturated liquid in there and it's vaporizing. So the key to it is understanding that pressure temperature curve on a PT diagram going somewhere between the critical point, and you're not going to ever get down to the triple point, but there you go. So you're dropping the pressure, it wants to go vaporize. Some of it will vaporize, the rest of it, all of it will just be cooled, lower temperature, so the energy is conserved. Now this is a chart. If you talk to somebody that's been in the HVAC industry, they go out to a house, they service your air conditioner, it's not working well, or they come out to the university, they have a big chiller. They're going to diagnose some problems. They're going to take some measurements, right? Like the blood pressure measurement when you see a doctor. Well, they're going to put on some pressure measurements and they're going to measure the pressure. And you only have really one high pressure, one low pressure in most systems. So they're going to measure that. And what they can do is they can tell from the pressure and some other temperature measurements, diagnose the system. And a lot of those will pull out a chart. They used to have it like a paper chart or a flip open. They would look at it, they'd look at their meter reading, they'd say, what refrigerant do I have? And they would be able to say, oh yeah, because right here for this is 134A, these are other refrigerants. As a function of temperature, they get the pressure. They're just reading the points. All this chart does is give you a sequence of points for the two-phase nature of the substance. So you can check it with some numbers in our table. They won't be perfectly the same. They'll be close in the vicinity. But here, 8 kilopascal pressure. It has a temperature, a saturation temperature, negative 24 degrees C. So it's like 8 kilopascal. Come over. You have the negative 24 degrees C. And that's all this chart is. This is a little old school. They still, some older gentlemen or people who are in this trade will still have these pull-out little charts. But now they have them on their cell phone. Apps do it. You could probably get an app for $2 that'll do this for you. You can get an app that'll do all the steam tables for about $2 as well. But don't tell your friends. Right? Did anybody see a technician come out with this type of gauge, hook it up? There's a lot of hoses they can hook up to the refrigerant system, but essentially one is colored red, one is colored blue. I wonder why. One for hot, one for cold. Which one is the condenser? The high pressure side, the hot side? What is the evaporator? The low pressure side, the cold side? And so basically this dial right here, you could see what is the pressure in the condenser and you can read off the pressure in the evaporator. These are very interesting to look at. I think I brought one to pass around. Yeah, I did. If anybody's interested, this is an old one. You can take the lid off. You can play. I usually show students this one because on the back, it's a particular mechanism for operation. It's the old. Anybody remember the name of this type of mechanism for measuring pressure? Oh, come on. I'm going to have to give the university back their money. They pay me. You know, the students take my classes and don't learn a thing. It's a French engineer, named after a French engineer a long time ago. Do you remember his last name? Borden. Borden tube. Right? Does that ring a bell? Once you mention it, yeah. And anyway, but you'll notice that you'll see on these, here's a blow up. And often what they have is they're measuring pressure and PSI. So here's 0 pressure, and as the needle goes around, 20, 40, 60, 80, 100 PSI. That's all it is measuring pressure, right? But there's a lot of information on this plot. What's on this plot? The pressure temperature data. Either the pressure temperature chart, like the HVAC people did in a tabular format, or the PT diagram, like in a plot. And so they have it for refrigerant 410A, refrigerant 12, refrigerant 22. What's in that light blue? 134A. They have it for 4 refrigerants. There's a lot of information on this. So what they're doing is they're saying, let's do this one. If I come over and the pressure's at 60 psi, that needle lines up like this. If I'm working refrigerant 410A, I can tell you the saturation temperature is 10 degrees. 10 degrees. And that's in what units? It's in F. It's in F. Makes sense? So that's what they're doing is you move up, you move there. So what they can do is they can diagnose to see what the temperature of the refrigerant is in that evaporator or in the condenser because of the pressure at which it's evaporating or condensing. And often it's out of whack because it's either overcharged or undercharged. Often undercharged. There's a slight leak in the system. All right. Or sometimes there'll be a blockage in the system. Then the pressure will be out of whack because of that. Today, guess what? Electronics have been invented. And so the modern HVAC technician will come out with something pretty sophisticated. Not only do they have the ability to pressure taps, high and low pressure, also hook up to a vacuum pump, also hook up to refrigerant to recharge or add in. There's a lot of ports here with a lot of valves. But also they have a digital display. They can probably thumb select their refrigerant. Oh, I'm at this refrigerant. And they also have detachable, this is a little coil here with this that clamps onto a line. There's one too. Guess what they're going to read with those little clamp onto the lines? Temperature. They're pretty sophisticated. So anyway, there's more to it, but really if you understand thermodynamics, this is easy. It's actually fun. It's actually fun. All right. Now, a lot of times we have a class and I don't have a lot of hands-on demonstrations, but this is a case where I can have a decent hands-on demonstration. In my hand right here is a can of Altex Dust Away. I purchased this just at the Altex store off 1604. If I have a dirty keyboard or I'm trying to clean off the CPU, I take the computer part, I want to, right, I blow it off. All right, here's a question. I have refrigerant in this can. I can feel it sloshing. You're going to come up here and feel it sloshing. And I want everybody else to do it if I have enough time. Can you feel it sloshing? What does it mean when it's sloshing? There's both liquid and vapor in this can. Is the liquid and vapor in this can in equilibrium? Are they at the same pressure? Are they at the same temperature? Now, I don't know the pressure of the refrigerant in this can, but can you guess or tell me pretty accurately the temperature of the refrigerant in this can? The temperature. This will throw students for a loop. They'll be thinking, well, if I don't know the pressure, how can I know the temperature? It's room temperature. It's been in this room for a long time. It's room temperature, about 75 degrees F. Okay. Now, somebody says, that'll actually allow me to calculate the pressure in here. You're absolutely right. It's two-phase. You could do a pretty good job using the tools to know the pressure in this can. And they say, don't leave in direct sunlight, don't leave in hot places, right? Because if the temperature goes up, what'll happen to the pressure? And you had fun, I know, on your grandfather's farm. When they were doing a little burn pile, you took a can and you flipped it in on the back side of that fire when nobody was looking. And all of a sudden, it went pow. And it was great excitement. And you had fun. How many people know what I'm talking about? Yeah, there's a lot of fun. My kids did it to me, too. Don't worry, I did it to my dad. But when I blow this out, I can hold it straight up top. Up at the top is the throttling device. When I pull back, it lets a little out, right? It's letting out vapor that's coming out the top. But just like a mischievous little child, a day after Christmas, my presents were all broke because I wanted to see how fast they really could go and how much weight they really could take and whether or not pounding them really, if they could. Anyway, they were all broke. We turned this thing upside down. Now where's the liquid? Right near the nozzle. When I pull this, what's going to happen? Take a look at the difference. Can you see the difference? What do you see right away? you see some white mist. What's that coming from? Where did it go? Why do we see the white? Is it the same phenomenon when you're in the winter and you exhale? The first cold winter day, you go outside and you go, ah, and it's so cool, right? Like, look at that, white smoke coming out of my mouth. What did you see? The humid exhaust coming out of your mouth meets the cold air, and it condenses some of it. So what happens is the moisture in the room got condensed for a little bit because of the cold refrigerant, and you saw that mist. Now, if you want to do a freezer burn, you blow that on your skin. Not recommended. Every HVAC technician has had frost burns, freezing burns on their skin. And unfortunately, some of them get them on their face, and one guy I worked with had it in his eye. Not good. It was a refrigerant leak that happened when he was young, and it spurted in his eye, and he had that pale, white, glossy look forever. So, but what I can do to prove to you that's super cold is a clean handkerchief, not used. And I can turn it like this and very carefully blow it in. And then I can give it to somebody and say, do you feel the temperature difference? Isn't it significant? Isn't it surprising? It's very surprising. He's very surprised his hands are clean. So what I'd like to do is stop now and let anybody come down and they can play with this if they haven't already. Thank you very much.